Hello Honors Chemistry and welcome to section 6.8, calculating empirical formulas. So this goes back again, right? Definitions that we learned in chapter 5, where an empirical formula, right, is the most reduced version, okay? That is the most reduced version of the chemical formula, right? Which we can then scale, right, up to a molecular formula, right? If we know what the appropriate relationship is between those terms, right? And if we think back to sections 6.6 and 6.7, we talked about how to come up with and use mass percent composition, right? And so it seems that there ought to be a way to go from percent composition to a chemical formula, right? Because in the land of what we do, right, that's going to be a more common thing, right? So here, this is a picture of the decomposition of water, where basically we have some water and we are running an electrical current through it, right? Note that this is not pure water, right? Going back to things we've talked about before, pure water does not have a lot of conductivity. So there are ions in here to facilitate the conductivity. And then we are decomposing the water as we run that electric current through it, right? Which means we're producing two different gases. Now, we can find out the respective masses of those gases, okay? And you'll actually learn how to do that in a couple of chapters, right? But once I know the masses of those gases, it would be convenient if we could then take that and figure out a chemical formula, right? So what this gives us is an analytical method to figure out the formulas of unknown substances, yes? So very useful. Okay, so let's go ahead and solve let's go over the steps, right? So step 1, right, we would need a percent, right? So we would take our percent and we would convert that to grams by assuming that we have a 100-gram sample, right? Step number 2, we would go from grams to moles of each element, right? And then step 3, we would take our moles and reduce, right? And then step number 4, we would scale up as needed to a whole number. As needed, right? And all of these steps are on an as needed basis, right? Because it just kind of depends on where we're starting, right? If I'm starting from percent, I need to start at step 1. If I'm starting from grams, I would just start at step 2, yes? So we start wherever it's necessary, right? If we already had moles, we would start at step 3, right? So it just kind of depends on where we are in the overall problem-solving process, okay? All right, so it says that we have a sample of a compound is decomposed, right? So again, analytical method, right? And it produces 165 grams of carbon. So 165 grams of carbon and 27.8 grams of hydrogen and 220.2 grams of oxygen. And we would like to know the empirical formula. Now, step 1, if we look back at our steps here, we're not starting from step 1 because we don't have percents, we have grams. So we need to get from grams to moles using ding, 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 molar mass, right? So 12.01 grams of carbon for every 1 mole of carbon, 1.01 grams of hydrogen for every 1 mole of hydrogen, and 16.00 grams of oxygen for every 1 mole of oxygen. Ta-da! Okay, so we have moles of each substance, and now, going back to the way, we'll go ahead and do it the way your book does it, right? We will turn this into a first level formula, right? So C, 13.74, H, 27.53, O, 13.76. Now we'll reduce by the smallest number, right? So 13.74, 13.74, 13.74, right? Which is always going to C1, H, is going to give us 2, and O is going to give us 1. Yes? And my formula is now CH2O. Yes, does that make sense? All right. Next up, we have ibuprofen, has the percent composition this and this and this, and we would like to know the empirical formula. So we have percents, right? And if we think here, right, that's step 1. So we need to get from percents to grams by assuming we have a 100-gram sample. Now, we could assume whatever we want, right? We could assume 5 grams. We could assume 1 gram. We could assume 500 grams. Doesn't matter. We use 100 grams, though, because, right, then these percents just become masses. So 75.69 grams of carbon, 8.80 grams of hydrogen, and 15.51 grams of oxygen. Using molar mass, and then we take our moles and then we reduce, and then we pick up with the next step. Okay, so if we follow the steps from the last problem, right, this is where we end up. Now, this is clearly 1. This one is clearly 1, right? This one is roundable to 9, yes? If we are within, say, 3/100ths of a whole number, right, we can round. This one now, not within 3/100ths, yes? 6.49 is approximately 6.5, and if we go back to that table in your guys' book, which I meant to include and I clearly did not, right, it gives us our rounding numbers, right? But all those rounding numbers, you can memorize them, yes, right? But really it's just the relationships between fractions, right? 6.5 is really a 1/2 fraction, yes? And if I have a 1/2, I can multiply by 2 to get a whole number, yes? To basically get rid of the denominator, or get rid of the part that makes it a fraction, yes? So what that means is I'm going to multiply by 2, but if I'm going to multiply by 2, everybody has to get multiplied by 2, which means now I have 6.5 times 2, which means C13, H18, O2. Yes, does that make sense? All right. And then if you go back to your book, right, all of them are based off fractions, right? So if you had 0.25, for example, right, 6.25, 25 is 1/4, so I would multiply by 4, right? Or if you had 6.33, 33 is 1/3, so we'd multiply by 3, right? So really it's just a matter of, do you understand the fractions? Now, let's say you aren't keen on fractions and you've forgotten the table. What could you do in the worst case scenario? Right, you guys all have calculators, so you could just sit there and multiply by 2, and then 3, and then 4, and so forth and so on until you got a whole number. I would not recommend that, right? Please feel free to sit down and chat with me, and we can go over that fraction thing again and see if that helps. But that's what you could do, right? That's all we're really doing, right? We're just shortcutting the process because of fractions. All right, one more. So we have a 1.56 gram sample of copper, right? Reacts with oxygen to form 1.95 grams of metal oxide, and I would like to know the formula of the metal oxide. Now, so I know I have 1.56 grams of copper, but if I want to know the formula of a metal oxide, I need to know how many grams of oxygen reacted. What am I going to have to employ? Correct, right? Law of conservation of mass, right? Where if I have 1.95 grams of metal oxide minus 1.56 grams of metal, right? That's going to give me 0.39 grams of oxygen, yes? And so, following the steps, we go from grams to moles using molar mass, and then we would take our moles and reduce by the smallest one. All right, and we end up with CuO. Now, here is one of those points of reference, right? If you look at all the rest of these, we kept a significant number of significant figures, right? So for example here, right, we had 3 sig figs, right, in each of these. Well, except for that 0.97, right? Here we had 4 sig figs, right? And the goal is 4 sig figs. Here, though, I shortcut it and I rounded it to only 2 sig figs, right? Which is why I get a little bit of, if I actually do this math here, I actually get 1.04, right? Which is 4/10 away from a whole number. But then if you extend it out 1 more sig fig or even 2, right, you'll see that you end up with a 1-to-1 ratio. Yes, but that's why rounding is important here, right? Otherwise, you might try to scale up to something weird, right? Now, here, this is a good example of why this is important, right? Copper is a type 2 metal, right? If I know that the formula is CuO, I also know that Cu has a charge of 2+ in this particular compound, right? Which can say something about the conditions under which this compound was formed, right? Versus if it said Cu2O, which would mean this would be copper 1+, right? So this is a useful method for helping to figure out, the charges of our type 2 metals. All right, thank you for listening. Be good, and I will see you soon in the last video where we talk about how we take this concept of empirical formula and with one more step we can solve for a molecular. All right, thank you for listening. Be good.